Hi all, hope you can hear me properly. Yeah. So myself Ramana, I work at Boson Motors from last 3 years. So I would like to present my work. Couple of what we're working at Boson Motors. One of the projects that we're working on is row centering for standard orchards, which is typically one of the main applications in agriculture industry. So I'll be talking about how we have solved that. What are the challenges that we're facing, and also what are the kind of tools we're using in ROS and in other things. So we'll be present. We'll be discussing with you and with inputs that we would like to take out of it. So again, to talk more about Boson Motors. So we are a fully electric autonomous off-road vehicles manufacturers and designers. So we are based off our headquartered in Chennai, and our R&D and software development is based off Tirupati, Andhra Pradesh, and our manufacturing is at Chennai. So we have two key products. One of, as I mentioned, as you can see on the slide, Boson truck. So which is we can say like fully electric truck, and it has got autonomous features inbuilt in. We have few features wherein we've been developing autonomous features on it, and few of them are follow me, where you drive in front of the where you walk in front of the vehicle and the vehicle follows you. So that is one of the applications we have. And we have a waypoint tracker, or you drive and playback feature, where you take the vehicle and do a safe path, and the vehicle tracks that very accurately with a 0.3 accuracy. And we also developed custom obstacle detection on top of it using vision and LiDAR based systems. And we're also working towards GPS environment at the moment. So we also have one more product, which is a stationary storage unit, so which is essentially a battery storage unit. So with the integration of battery storage units from the solar systems and Boson truck, we envision for a future of agriculture where you don't need a grid, like you don't need to have a power from some big power plant and all. You will have off the cell power. You can get it from the solar, and you can charge to the vehicle, and the vehicle moves anywhere in the fields. Especially our target is to work in the agriculture domain where electricity may not be possible all the time, right? So moving ahead, so I'll be discussing the agenda. So it's essentially like what I'm gonna do and how are the things. So to move ahead, so what is that we are working as one of the projects? What is that we're working on? So one of that was in a row centering in standard orchards. So it is essentially like, so what you do in if you're driving in on the road vehicle, it is as important as you're driving in the lanes, right? You're always in between the lines on the road. So essentially what you do, something like that system you should have in order to, because in the roads you have lanes, and in the agriculture farms or orchards you would have trees on your left and right sides. You need to drive in the center properly so that you would not hit those trees. And given that you have implements at your back end, because then Bossa trucks would obviously have implements such as spraying, for mowing and other, for carrying goods and all, which we might have few implements on the back end. So we would like to go in the center as center as possible, not to hit the trees, so that we can have an efficient navigation throughout our orchard. Why it is important is it is very repetitive and it is boring. Every day you have to do. One of the applications is watering we are envisioning. So in the US like farms, you need to water it every day. That watering is not just for the growth of the farm, but for other features we will be using it. So these are few applications that we envision: so spraying, mowing, watering, and inspections, and carrying goods in agriculture essentially. So again, to going ahead, I would like to discuss more about the sensor stack we have on our vehicle. So we have RTK GPS dual antenna RTK GPS dual antenna configuration in our vehicle, which we use for the better stability in our heading. And another one we use is a 3D LiDAR, which you all know, we are working on off-roads. It makes sense using 3D LiDAR. And we are also using stereo camera, which we would essentially using for other purposes. And coming back to the software stack, so we're using ROS NeoChip as a main communication platform between the nodes and the sensors, and all of our stack is implemented on top of it. And again, the tools C++ and Linux. And tools again, since we're using ROS, there is no reason, we have to use Rviz and Foxglove. And we also have a simulation version of our vehicle, which works with our own, like we have created our own version of it taken from open source, customized it for our agriculture application, and we're creating own custom simulation environment to operate and test our code. So again, I would like to briefly tell about our methodology we used in achieving this row centering. So the methodology involves construct local map, cloud construction, ransack parallel fitting, and this is the first part. And the second part involves is a constant speed and incremental steering trajectory generation. That is essentially how you generate trajectories out of your kinematic. Again, I'll explain it later. So again, a DWL trajectory generation, then evaluation using using cost collisions, about collisions and how close to the center line. And we use a pure pursuit controller as a low-level controller to control the vehicle to find a steering angle and speed so that the vehicle moves, follows the trajectory. Okay, moving ahead. So how do I construct the local map of my environment? So for that, we are using a very simple methodology where we convert all of our sensor points from sensor frame to a global frame, which in our case is a map frame. Then we do a voxel filter and a point crop box filter from PCL library to create a consistent window-sized local map around our vehicle, which then will be used for our lane fitting algorithm. So the lane fitting algorithm that we use today, that we use in this application is a ransack. So ransack essentially is a ransom. It is used to fit data points to a geometry model that you'd like to fit. That your world would much look like. In my case, my world is much of looking like a line, which in our case I have a left and right line. So I'm using a parallel line fitting method using in the ransack version. So how it works is I have points, then I would select 2 points on my left to my vehicle. Again, I'd find 2 points on the right. So I'd find number of layers. I do this operation for a couple of number of iterations, and I would find the best line equations, which essentially gives me more number of layers. So that is one of the few things that what's happening inside of this algorithm. And then once I have this in layers, I'm using a linear least square method to fit better. To fit a line which best fits my linear. My in layers. So then I'm using essentially I'm using moving average filter to actually transition, to proper transition between the line to line in every iteration of my loop. So this is on the, as I have mentioned, this is the first part. So the second part involves creating a GWL trajectories, which are, which you can see on the right side. Okay, how can I go backwards? So again, to my previous discussion, you see the local point cloud and the lines fitted on the screenshot. You see green color and a red color. So essentially, whatsoever is showing as a green color box, which is essentially my robot's footprint. Okay, moving ahead. So here I'll generate constant speed and incremental trajectories using DWL techniques. Using my vehicle's bicycle model equation, I would generate for a fixed length how would my vehicle would take given this is my speed and this is my steering angle. How would my vehicle would take given my vehicle has got fixed steering limits, that is from -30 to 30. So I would generate these trajectories. Then I would use again, I'm using a CostMap 2D package in the ROS, which is already implemented, and I'm using 3D point cloud to populate that point cloud populate that cost map, and then I'm using I'm checking those trajectories that I have discussed so far, like how many trajectories are are going to be collided and which are collision free. So out of this you can see on the screenshot. So in the previous slide I have a lot of trajectories, and in the present slide I have a few trajectories that, which are collision free with respect to my cost map. Again, my footprint details and all encoded in this cost map params. Again, is inflation radius and all. So moving ahead, again I have few trajectories which are collision free. How do I select one out of it? So as I have mentioned, I have detected the lines in the step one. So I'd use that line here to score to evaluate which one is the best one out of the trajectories that I have shown before. So you can here the cost are the cost which defines the are two factors. One is how close my trajectory to my central line and some, I mean, which is in the same direction of my vehicle. So given that in the screenshot you can see the line, the path which is represented as an axis is selected as the final trajectory that is to be sent to the vehicle. So at the end, I have a pure pursuit controller which is essentially finds steering angle, and steering angle, given that I have a local trajectory from my previous step, I'll forward this to pure pursuit controller. It finds a lookout point and finds what is the best steering angle that what is the steering angle that the vehicle can take to maneuver that to that point. So this is a pure pursuit controller we use to find out the steering angle. So how do you validate? You have a methodology. How do you validate your stuff is working or not? So again, we use an extensive use of Gazebo simulator with our custom world. So you can see one of our vehicle on the screenshot. Again, it is a skeleton vehicle, and you see the Gazebo simulate, environment where you have a orchard like thing which is represented with the trees. So we have a setup where with a single argument you can just switch between real world and simulation, real world and the simulation. So that way, once after we develop code and test in the simulator, it is very easy for us to test and validate our algorithms on the real platform and come back with the results. Do some post processing on it to see how the system went. So again, real world testings. I think the video should play. Can you help me play this video? Can you help me play this video? Sorry, this one. This one. Previous one. Yeah. I'm not touching. Yeah. So whatever discussed so far, the methodology that we used and how do we generate. So this is a real world test that we have done in San Jose, California. Again, our headquartered in all of our testing is mostly happens in US and India. And this is one of the Rviz visualization, the method that we have used in real world testing on the real farm based of, that farm is in San Jose, California, something like that. You see whatever the white path you see, that is save path. We're not handling the turning spot yet at the moment. It is not, we'll be doing it subsequently. And whatsoever you're seeing as a green color path, so that is the center line. And we see we're also handling the turnings, which is the Dubins based turnings again. So again, can you play this video? So this is a live video of our vehicle on the. Please, can you? Would you mind placing this video? This is our drone photos and other visualization of how the vehicle is centering in the real farm testings. So let's see. And again, to continue, we have a yeah. So here you can see our vehicle. It's actually centering, or actually going through the arcades relatively at a good pace. And whatever the algorithms we develop, this is how we test, both in the simulation and the real world. Yeah. So moving ahead, what are the challenges and the future scope out of this? So we would like to use ladder and camera based SLAM to, so that we would continue our work under canopies of the trees. Currently, most of the work is based off RTK GPS and GPS stuff. So we'd like to continue our work towards GPS generated environment. And especially for the centering, we'd like to work on auto turnings using Dubins, read seeps, and A-star like things. Again, it is under development. We have some POCs that have been part. And again, we would like to envision this project as an end-to-end archer navigation framework using mapping and auto routing methods. So that is how we are envisioning this project. And again, the few methods that we would like to incorporate is we would do an octogrid mapping covering all the rows, and we would use fields to cover routing or routing techniques to generate best routes for that vehicle can serve for the next routes and something. So again, with that is all I have. If you have any questions, again, thank you so much for your call. Things. So again, if you have any questions, I'm free to help you out. And one more thing is we are hiring. We're actively looking for the talent. Anyone, if you're interested, please reach out at this HR at Bosen Motors. And my email is at ramana@bosenmotors. So we'll take it forward. Any questions? And one more thing, we have a really great vehicle. We have a great scope. So let's build great products with ROSCon Rastu together. Yeah.
Thank you so much. And you guys heard them. Boson Motors is hiring. So in case any of you is interested in working with them, feel free to reach out to them. Thank you so much again from the presentation. Guys, let's